Hi, my name is Cornelius, and I'm presenting on our work on receding horizon and heuristic-based logic geometric programming for task and motion planning. Let's consider this task where several robots are set up in a row and the target is to move the red object from its initial position to the green tray, our goal. Assume each robot is provided with a set of primitive manipulation skills, such as grabbing and placing objects, along with a symbolic description of the current state and a desired goal state. With this information, our system must then decide how each of the robots should use any of their skills at each step to move the object to the goal. While this problem setting may be easy to solve for a single object, it becomes more and more difficult when increasing the number of objects that shall be moved. This is since more and more actions will be necessary to reach the goal, and crucially, because the combinatorial complexity of possible action sequences increases rapidly with the number of objects. Thus, a setting that includes only 3 or 4 objects is already very hard to solve for current task and motion planning approaches. Our goal in this work is to overcome these difficulties and enable long-term planning in tasks with multiple agents and objects. Our framework for this is built on the logic geometric programming paradigm for task and motion planning, which we abbreviate by LGP. We improve LGP by using geometry-based heuristics that approximate the remaining costs to reach the goal for a given symbolic state. This approach enables us to eliminate geometrically infeasible action sequences from the set of possible solutions without expensive costs to the motion planner. Secondly, we present a receding horizon formulation of LGP. The benefit of this approach is that large-scale problems can be partitioned into computationally tractable subproblems, which enables to further increase the complexity of tasks that are successfully being planned. Let's have a look at our contributions in more detail. Typically, the LGP motion planner would be used on every logically valid action sequence. But for some of these action sequences, it may be clear that they are physically impossible to execute without using a motion planner to confirm this. Consider the first example on this slide of the rightmost robot grasping a red object. Since the robot cannot move, and any red object is too far away from the robot, there will be no solution that involves grasping an object with the rightmost robot when the object is on the leftmost tray. Similarly, the second example on the slide shows a crawler robot reaching towards the red and yellow objects, which are clearly out of reach in the current state. In both of these examples, it's possible to tell that any action sequence, including these actions, will not be part of a valid solution, simply based on the symbolic state. To exploit this idea, we introduced geometry-based heuristics, which estimate the costs to reach the goal state after executing a given action on symbolic planning level. Using these heuristics, solutions that are likely to be infeasible can be ruled out early during symbolic planning. For example, on the right-hand side, we can look back at the example I just gave and see that using the step heuristic, we can tell that stepping from the current tile onto the topmost red tile will never be possible, so it's pruned from the search tree by the heuristic. In similar fashion, our work presents one heuristic per symbolic action, which are task-independent and can be mixed and matched based on your needs. To plan long horizon tasks, we present a receding horizon formulation of LGP, which iteratively plans actions for a given number of steps until the goal is reached. Using such a receding horizon approach enables us to break down large-scale problems into computationally tractable subproblems. Furthermore, this allows to react to changes in dynamic environments as planning can be performed adaptively. We start planning with some initial kinematic state of the environment and a set of symbolic goals. The first step in each planning iteration now is to find symbolic solutions to the whole task given the current state. In this step, we continuously estimate the heuristic costs and prune geometrically infeasible solutions from the search tree during symbolic planning. Given a symbolic solution for the entire planning problem, we select the next H actions from the solution action sequence according to our planning horizon H. Provided with such an action sequence, or skeleton, the motion optimizer then tries to find a feasible motion sequence corresponding to these actions. If no solution is found, then the symbolic planner tries to find another action sequence. If a solution is found, but the symbolic goal is not reached yet, the actions are executed and the next planning iteration is started based on the current kinematic state of the environment. This procedure is repeated until eventually the symbolic goal state is reached and the task is completed. Our experimental results show that our framework enables long horizon planning for a variety of tasks from various domains. The presented planner enables planning more complex tasks that include up to 16 times more objects than what can be planned with the conventional LGP solver, as we can see in this table. We also show that our framework is very efficient, reducing planning times by an order of magnitude. The generalization of our method is demonstrated on a variety of task and motion planning problems, which include a pick-and-place task with multiple agents. In this task, multiple objects have to be placed on a goal tray. A parkour task in which a crawler-type robot must navigate towards a target that is behind multiple obstacles. This problem is challenging due to the number of actions that need to be executed to reach the goal. And a task including multiple modular robots that must be connected to guarantee an efficient solution of the task. This problem is challenging as the planner must recognize that connecting two robot modules is beneficial for task completion. Overall, by leveraging geometry-based heuristics and receding horizon planning, we are able to solve more complex long horizon tasks than previous planners. We demonstrate that this approach generalizes well to a set of different scenarios, including multiple agents and modular robots. For more information on our heuristics and planning algorithm, please see our paper. Thank you very much.